In the first half of this chapter, we looked at horizontally launched projectiles. Horizontally launched projectiles are a little bit easier to work with because the initial vertical velocity is 0. What we're going to look at now is the much more common case, which is projectiles that are launched at an angle, that have both an initial horizontal and an initial vertical velocity. When you're dealing with projectiles launched at an angle, you will commonly have something like a projectile launched at 20 meters per second at an angle of 30 degrees. The first step in any projectile problem is to get your initial horizontal and vertical velocity. To do this, when you have a vector, a velocity vector that is in polar notation, you're going to have to convert it into its rectangular notation, the horizontal x and the vertical y. So the first step is a conversion from that horizontal polar notation to rectangular notation. Once you have it in rectangular notation, then you can set up your two columns again, horizontal column and a vertical column, and set up displacement and velocity equations. Once you have those columns set up, you can solve for the needed variables. A couple of key things that we'll see in the lab that we do later in this quarter is that projectiles launched at an angle of 45 degrees will travel the furthest. That's an important point to remember. And that if two angles add up to 90 degrees, two projectiles fired at the same velocity at those two angles will go the exact same distance. So if one is fired at 60 degrees and one is fired at 30 degrees, they will both land the same distance away. If one's fired at 10 and one at 80, they'll both land the same distance away. If it adds up to 90 degrees, the range or horizontal distance will be the same. So let's look at an example of a projectile. Here we know the components. It's going vertically upwards at 30 meters per second and horizontally at 10 meters per second. A couple of things to remember with projectiles. One, velocity vertical is still, or acceleration vertical is still 9.81 meters per second squared going down. The horizontal acceleration is still always 0. So as this goes up, after 1 second, it will travel 10 meters to the right because it's traveling at 10 meters per second. It will travel up 25 meters and will now be going a velocity of 20 meters per second. So in this case, our velocity would now be 20 meters per second. It started at 30. Now it's at 20. It's decreased by 9.81 or 10 meters per second. The next second, it will go another 10 meters. So we've gone from 10 now to 20 meters horizontally because it's going at 10 meters per second. The horizontal velocity is still 10 meters per second to the right. Vertically, it's gone from 30 to 20. Now it's going to be traveling at 10 meters per second going up. So it's slowed down from 30 to 20, 20 to 10. If you calculate the delta x, that would be 40 meters up in the air. After 3 seconds, the velocity horizontally will still be 10 meters per second. So we'll have gone 10 meters, 20 meters, it will now be at 30 meters. It will have traveled up, it's slowing down, so it's gone from 30 meters per second to 20 meters per second to 10 meters per second, and now it is traveling at a velocity of 0 meters per second vertically. So if you threw a ball straight up in the air at 30 meters per second, it would be at this point. If you threw a ball horizontally at 10 meters per second, it would be at this point, down here. So these two are just vertical and just horizontal. When you put them together, you have the location of the ball. And this would be our peak, the highest point in the path. And the velocity vertically at the peak will be 0, just like we did with other free fall problems. Now it's going to start going back down. The velocity vertically will now be negative 10 meters per second. So it's gone from 0, it's increasing its velocity at 10 meters per second down because the acceleration is down 10 or 9.8. And it's gone 10, 20, 30, 40 meters horizontally, 10 meters per second. After another second, 5 seconds in, the velocity on the horizontal will now be negative 20. And we'll have gone 10, 20, 30, 40, 50 meters horizontally. And after 6 seconds, it will have reached the ground. It will be 60 meters away, and our vertical velocity will now be negative 30 meters per second. So it started at 30, went from 30 to 20 to 10 to 0 at the peak. At this point, it was a vertical velocity of 0, and then starts coming back down, negative 10, negative 20, and now at negative 30 as it hits the ground again. Horizontally, it's still going 10 meters per second, and it's covered 60 meters. So if we work our way back through this, you can see, started at 30, vertically 20, after 1 second, 10, 0, negative 10, negative 20, negative 30. Horizontally, goes 10 meters, 20 meters, 30 meters, 40 meters, 50 meters, 60 meters. And you'll see at the peak took 3 seconds, so it takes another 3 seconds for it to hit the ground. A couple of things to remember. The vertical acceleration will be 9.81 meters per second squared going down. The vertical acceleration will be 0 meters per second squared. You must pay attention to direction in these cases because you have both a vertical and a horizontal motion. The vertical motion is both up and down. You must make one direction positive, one direction negative. The common thing that we will most commonly do in solving these problems is to make up positive and down negative. We'll make to the right positive because that's going to be pretty much our only horizontal direction. The vertical velocity at the peak is always 0 meters per second. That's a very important piece of information to remember. The vertical velocity that returns to the original height, the ground, or whatever original height it started from, is always going to be the opposite of the initial vertical velocity. So the same value in the opposite direction. So the starting value was positive 30, the ending value was negative 30. And the time to the original height or the ground is twice the time to the peak. So if you solve the time to the peak, you can always double that to get the total time in the air. The common questions you'll be solving with projectiles at an angle fall into 4 categories. How long does it take to reach the peak? What you're solving for there is the time to the peak. You can remember that the vertical final velocity will be 0 at that point. That's a key thing to remember when solving that very easy. How high does the object go at the peak? That's the vertical displacement peak. It's the time to the peak. How long is it in the air? This is the time to return to the original height of the ground. And remember, the vertical final velocity at that point will be equal to the negative of the initial velocity. How far does the object go, or what is the object's range? That is the horizontal displacement when it returns to the ground. These two at the end are for the total of the projectile. These two are for the peak. Remember, the time for the total trip will be twice the time to the peak. So in the next video, we'll do a couple of example problems, 3 example problems of projectiles launched at an angle, so you can see the steps going into solving those.